All right, let's look at this example. We want the area between the red curve that is going to be given by this cubic function here and the blue curve that is given by this quadratic function here. All right, and so we want to find the area between them. So the first step is to set them equal to each other as we did before. Let's do that here. So intersection points. Let's call it just intersections. Looks almost like intercepts, but let's say intersections there. So let's set them equal to each other. So start with that, x cubed minus 4x squared plus 3x equal to x squared minus 3x. And from the previous video, now we know we're going to subtract the terms on the right hand side on the left. Well, on both sides, we're going to end up subtracting on the left. So subtracting x squared on both sides, I want to first get negative x squared, 4x squared minus x squared is going to be negative 5x squared. Now I have plus 3x, and then I'm going to add 3x on both sides, so it's going to be plus 6x equals 0. So now it's a matter we have to factor. So we factor firstly an x. That gives us the following. And now to find the other intercepts, or the other intersection points in this case, actually intercepts for this function, but intersection points, we can factor again and get x minus 2, x minus 3. And that gives us the intersection point 0, 2, and 3, as we see from the graph. All right, so those are going to be our intersection points. So now we have to be careful to set our integrals correctly. So the integrals, the area between the two curves is going to be given by the integrals, firstly from 0 to 2, from the first intersection point to the second. And which is the function that goes on top there? The function that goes on top there is going to be your red function, which corresponds to the cubic function here. So x cubed minus 4x squared plus 3x is going to be minus the one that goes on bottom, which is going to be the blue one that here I have with green because I didn't have the blue there. And that function is the quadratic function. It's going to be x squared. And by the way, whenever you're going to subtract there, add parentheses or brackets so you don't mess up the sign. If I would have just written it without a bracket there, I would have had this minus 3x, but in reality it's minus negative, which is going to be plus. So that's going to change the sign, so just be careful. So that's going to be my first area here. Now I gotta add the next one, so the next area, I'm gonna do plus, and I wanna have the area from 2 to 3. And from 2 to 3, now the only thing we have to be careful is that the top function is going to be the quadratic. So I'm gonna do x squared minus 3x, and then I'm gonna subtract the one in the bottom, which is gonna be the cubic function, so x cubed minus 4x squared plus 3x dx. And now I'm going to do some, open something else. There. Barely have any space. I didn't realize there's an edit button there. All right, anyways, now we just have to collect terms and integrate. So from 0 to 2, x cubed, there's no other cube, so we copy that one. Minus 4x squared minus x squared, so it'll be minus 5x squared when I collect those like terms. And then plus 3x minus negative is going to be plus 6x, 3 plus 3. And then I'm going to have the same function, but it's going to be always negative numbers, going from 2 to 3. So when you do this one, you're going to have negative x cubed. Then the other one will be minus negative is going to be 4x squared plus x squared is going to be plus. It's just going to be the same function, except you're going to change the signs. Some people, what they do is just they put a minus here and then copy the same function, which is just saves you a step. But right now, since I'm just explaining to you how to do it, I'm just not going to do that. And that integral right here, the second integral, by the way, takes care of this area here. So from 0 to 2, you get this one, and then from 2 to 3, you get the rest of the area. All right, and now it's just a matter of integrating and evaluating. So let's go ahead and do that real quick. So here I get x to the 4th over 4 minus 5/3 of x cubed plus this is going to be x squared over 2, which is going to result on a 3 here. 3x squared. All of it between 0 and 2. And then minus or plus. No, let's do minus. Put it here. Minus. I'm going to copy the same integral. I'll have to continue here. All of it between 2 and 3. And then once you compute that value, you just subtract it from the other one we obtained. All right, so let me do the numbers quickly here, and I'll just write the answer. All right, so we get 37/12 for that one. All right, so here we're going to look at the situation where we have functions given in as x as a function of y. Not quite implicit, but actually written in the, instead of y as a function of x, x is a function of y. And this is going to be useful. It doesn't seem like it would be too useful, but it's going to be useful later on when we do volumes and solids of revolution and surface of revolution. It'll be useful to set some integrals in that form. So let's take a look at what happens here. So if you were to compute your wanted to compute your area there, and you would draw, let me draw something a bit darker. You would draw your rectangles in this direction, like so. I'm trying to, maybe I should zoom in when I'm going to draw. Probably a good idea. Let's go ahead and do that. That would be quite helpful. So you draw your rectangles in this direction. Much better. And so forth and so on. So what happens is what you're fixing now is not an x. You're fixing a y value here. And this distance here is going to be distance between, well, the coordinate here is going to be x comma y, but for this one in particular, x is equal to y, so you get y comma y. And here, this point is going to be of the form x comma y, but in this particular case, x is going to be y cubed, as is given here. So it's going to be y cubed comma y. So for a fixed value of y, our x coordinate here, the distance between this point and this point is going to be given by the distance between the x coordinate, which is going to be y minus y cubed. And so what that tells us is that we can set this integral. So I'm going to do just this first area first, and I'm going to skip the calculation of the intersection points are going to be between 0 and 1. So that first area is going to be given by, and let me change now color to this one. That first area is going to be given as the integral from 0 to 1. And now the height, quote unquote, of that, which would be really the width of that rectangle, is going to be given by y minus y cubed. And now what would correspond to the width, you're going to have a dy, so a differential of y width for that rectangle, or in the way we have it written, it looks more like a height. But so it's going to be the distance of the y, that's going to give you the length, and then the dy gives you the thickness of each rectangle, and you integrate from 0 to 1, that gives you this first area. There's symmetry. These two functions are symmetric with respect to the origin, so really this area is going to turn out to be the same, but I'm going to just write it out so we're clear. This one will go from -1 to 1, and when you're drawing your rectangles here, now you're going, you always subtract from right to left, because that gives you a positive height. So the one on the right is going to be y cubed, and the y on the left is going to be y. So this is going to become y cubed minus y. So whenever you're computing heights or lengths here, you want to make them positive. So you're going to go from right to left or from top to bottom. That's why when we were doing vertical rectangles, we said from the one on top minus the one on the bottom. That's just because that guarantees that your rectangles will have a positive height. All right, so in this case, when you're doing horizontal, you're going to go from right to left. And so one single rectangle would look like that. In this case, you have a dy, and that's going to allow you to set up your integral. Technically, it's a delta y, but just so you can see where things are coming from, this is going to give the area of this one rectangle would be y cubed minus y times dy. There's a delta y, and then you would have to do a limit process to actually get exactly the integral we have. Nonetheless, the idea I want to convey is that you can see those quantities like that. And setting up these areas in this fashion is going to be quite useful for whenever we do surfaces or solids of revolution, which is something that a lot of people have issues with. Nonetheless, let's compute this one at this point. So the integral here will be y squared over 2 minus y to the 4th over 4 from 0 to 1. Let's do plus y to the 4th over 4 minus, let's put this in a parenthesis, y squared over 2. We're going to evaluate all these between negative 1 and 0. I bet you guys were wondering. We're going from -1 to 0 right there. So if you were wondering, write it in the comments or something. And I'm sorry for not realizing that I put a 1 in place of a 0. Anyway, so now we can compute it. And for this one, we're going to have 1/2 minus 1/4 is going to give us a 1/4 altogether. You can plug the numbers and verify. And here we're going to have a 0 again, minus, and then when we do here, we get a -1/4. So it's going to be plus 1/4 again. So we're going to have that the area turns out to be 1/2. 1/2 unit squares, depending on what units we'll be using, but that will give us our area for that region right there. All right, we'll stop the video right here, and I think this is sufficient for the whole section, but if you have any questions, please do let me know. I can create another video as well.